Hello everyone, I'm very excited because we have this interesting problem right here. I to the power I is equal to what? Before we start, if you're new on my channel, please go ahead and hit the subscribe button, like the video, comment, and share. Thanks a lot for subscribing. Now let's get right into it. If we can write A as e to the power ln of A, then we can also write I as e to the power ln of I. So let's go ahead and then replace this I with this. So we're going to have e to the power ln of I or to the power I. From here, let's apply the power rule that a to the power m or to the power n is the same as a to the power n or to the power m. So it's a matter of interchanging the positions of m and n. Great. So from here, we're going to have e to the power I or to the power ln of I. And this is where the problem becomes interesting. What is the value of ln of I? Great. Now let's move straight away to the complex plane. I'm going to draw a complex plane here. And as always, the horizontal component, we're going to have the real part. And then the vertical axis, we're going to have the imaginary part. Now the distance from the origin to this point, let's call it A. Then the distance from the origin to this point, let's call it B. Now if we trace this line just like this, then we trace this one just like this, where they intersect, let's call it point Z, which of course is equal to A plus BI. That is the simple complex equation. Now, if we draw a straight line from the origin all the way to line Z, then we're going to have our R here. Then we see that R has created a certain angle along the horizontal component. Let's call that angle theta. Then we have a right angle here. Now let's go ahead and then resolve this. On the horizontal component, we're going to have A is equal to R cos theta. Likewise, on the vertical component, we're going to have B is equal to R sine theta. Now let's go ahead and then replace the whole of this one into this equation right here. So we will have Z is equal to A, where A is R cos theta, then plus I, B, where B is R sine theta. Now let's take R out. In other words, let's factor out R. So we're going to have cos theta right here, then plus I sine theta. And guess what is inside the parentheses? Euler's equation. Euler's equation is given by e to the power I theta, which is equal to the whole of this one. Then we are left with this R here. So I'm going to bring it right here. And this is equal to Z. Very interesting. Let's name this one equation 1. Then from equation 1, let's introduce ln on each side of the equation. So we're going to have r e to the power I theta here. Then we'll have ln of z is equal to, this is natural log, so we can split it as ln of r plus ln of e to the power I theta. Let me put this one in parentheses actually. So we have ln of z is equal to ln of r plus. Now we see that this ln and then this e won't do each other. So here we are left with I theta. That is great. Let's call this equation 2. Now having known what ln of z is, then straight away we can find our ln of I using equation 2. So our ln of I will be equal to ln of r plus I theta. Very great. Now let's represent this on a complex plane. So I'm going to have to draw a complex plane right here. And as always, on the horizontal axis, we have the real part. Then the vertical axis, we have the imaginary part. Now, the point over here is simply I, that is 1I. So the distance from the origin all the way to I is going to be 1, which is equal to R. Then this point over here, the distance from this point to the origin is also 1. Then the angle from here all the way to this point is going to be 90 degrees, which is pi over 2. So let me write theta is equal to pi over 2. But the truth of the matter is that we can keep on rotating in so many ways, so we can have different angles for theta. Therefore, let's go ahead and then add 2n pi, where n is an integer, just like that. So we know what theta is, we know what r is. Let's go ahead and then replace them into this nice equation right here. So we're going to have ln of I is equal to ln of 1 plus I times theta, where theta is pi divided by 2 plus 2n pi. Great. So we have ln of I is equal to, now the whole of this one will give us 0, then plus what we have here. So let me keep this one here. I times pi divided by 2 plus 2n pi. So basically, this is the equation that we have for ln of I. So let's go ahead and then replace it into our main problem right here. So we're going to have e to the power I times the whole of this one. That is I times pi over 2 plus 2n pi. Now we can simplify this further. I times I, that is -1. So we're going to have e to the power -1 times pi divided by 2 plus 2n pi. And guess what? You can keep it here, or you can just distribute this negative. So we're going to have e to the power minus pi divided by 2 minus 2n pi. And guess what? This is the final answer. Now wait, wait. Let's go ahead and then assume some values for n. But remember, n is an integer. So we're going to have n, then some values that we will be getting when we put in n. So let's say n is -1, n is 0, n is +1. But remember, it keeps on going just like that. So let me just end it here. So if we replace -1 into this expression right here, we're going to have e to the power 3 pi divided by 2. Then if you put if you put 0 into this expression here, we're going to have e to the power -pi divided by 2. Likewise, if you put 1, we're going to have -5 pi divided by 2. So you see that we keep on getting certain values for the expression given any n value. And if you use calculators for this one, we're going to have approximately 111.3178. Then here we're going to have 0.2079. Then this point we have 0.000388, and it keeps on going just like that. So that is pretty much it. I hope you found this video useful. Please subscribe to my channel if you are new, and also like, comment, and share. See you again on the next video. Take care.